Hey everyone, let's dive into this Leetcode problem. It sounds a bit complicated at first, but we'll break it down together step by step. The goal is to get the highest score possible by applying a specific operation a limited number of times. Let's see how it works. Alright, here's the official description. Don't worry about reading every word. The main idea is, we start with a score of 1. We have a list of positive numbers called, we can perform an operation up to times. The operation is, first, choose a continuous chunk, a subarray, from the list that we haven't picked before. Second, look inside that chunk and find the number with the highest prime score. What's a prime score? It's just how many different prime numbers multiply together to make that number. For example, 12 is 2 times 2 times 3. The different primes are 2 and 3, so the prime score is 2. If there's a tie for the highest prime score, we pick the number that shows up earliest in the chunk, smallest index. Finally, we multiply our current total score by the number we picked. We want the biggest final score possible, remembering to use modulo arithmetic because the score can get huge. Let's walk through the first example. We have numbers 8, 3, 9, 3, 8, and we can do the operation twice, k equals 2. First, let's figure out the prime scores. 8 is 222, only prime is 2, score equals 1. 3 is prime, score equals 1. 9 is 33, only prime is 3, score equals 1. So all numbers here have a prime score of 1. Operation 1. Let's pick the subarray. 8. The only number is 8. Its prime score is 1. So we multiply our score, initially 1, by 8. Score is now 1, 8, equals 8. Operation 2. Let's pick the subarray. 8, 3, 9, 3. The numbers are 8, 3, 9, 3. All have prime score 1. The rule says, if there's a tie, pick the one with the smallest index. That's the first 8, index 0, or the 3, index 1. Wait, the explanation picks 2, 2, which is just nums 2, equals 9. Okay, let's follow their example. Choose subarray, 9. Element is 9. Score becomes 1, 9 equals 9. Now, choose subarray, 8, 3, 9, 3. Elements 8, 3, 9, 3, all have prime score 1. Smallest index wins. That's 8 at index 0. Oh wait, the example says they choose 9 again? Let's reread the example text carefully. Okay, the example explanation is slightly different. First, choose subarray. 2, 2, meaning just nums, 2, which is 9. The element is 9. Prime score 1. Score becomes 1, 9 equals 9. Second, choose subarray. 2, 3, meaning nums 2, nums 3. These are 9 and 3. Both have prime score 1. Smallest index wins, so we choose 9. At index 2, score becomes 9, 9 equals 81. This works. The key is choosing the subarrays carefully. So the first idea might be, okay, let's list every possible continuous chunk of the numbers. For each chunk, find the special number based on the prime score rule, then somehow figure out the best sequence of chunk choices. But wow, the number of chunks can be huge, like n squared where n is the length of the list. And then we have to pick k of them? That sounds way too slow for a typical programming contest limit. We probably need a smarter approach. Instead of thinking about subarrays first, let's flip it around. Let's think about each number in the original list. For a specific number, say nums, can we figure out how many different subarrays would end up picking this nums as their special number? If we could calculate this influence count for every number, we'd know how valuable each number is. How do we find that influence count? A number nums gets chosen by a subarray if it has the highest prime score in that subarray with the tiebreaker rule. This means its influence extends leftwards until it hits a number with an equal or higher prime score, and rightwards until it hits a number with a strictly higher prime score. We can find these boundaries efficiently using a technique called a monotonic stack. Once we know the left boundary index L and right boundary index R, the number of subarrays that would pick nums is simply how far left it reaches times how far right it reaches, which is IL, RI. After we calculate this count for every number, we have pairs of value, count. To maximize the score, we should greedily use the numbers with the highest value first, applying the operation as many times as its calculated count allows until we've done k operations. Okay, here's the complete Python code that implements this smarter approach. It might look a bit dense, but don't worry. We'll break down the main parts on the next few slides to see what each section is doing. First up, we need those prime scores for every number in our input list. We find the biggest number in the input first. Then, we use a method similar to the sieve of Eratosthenes. We iterate from 2 up to the maximum value. For each prime number p we find, we go through all its multiples and increase their prime score count by 1. This efficiently pre-calculates the number of distinct prime factors for all numbers, up to the maximum value we'll encounter. Finally, we create a scores list that maps the original nums to their calculated prime scores. This is the clever part using stacks. We do 2 passes. The first pass goes left to right. It uses a stack to find, for each element I, the index of the nearest element to its left, that has a prime score greater than or equal to the score at I. The second pass goes right to left, finding the nearest element to the right, with a prime score strictly greater than the score at I. These left and right boundaries define the score zone of influence for each number based on the problem's rules. Notice the slight difference in the comparison operators, less than vs less than smiley face. This handles the tie-breaking rule correctly. Now that we have the left and right boundaries for each index I, we can calculate how many subarrays would choose nums. Remember, it's the distance to the left boundary times the distance to the right boundary. I left, right I. We store this count along with the actual value nums as a pair. Since we want to maximize the score, we should prioritize multiplying by the largest numbers. So we sort these value count pairs based on the value in descending order, biggest values first. Finally, we calculate the result. We start with a score of 1. We go through our sorted list of value count pairs. For each pair, we figure out how many times we can use this value. It's the minimum of its calculated count and the remaining operations k we have left. We calculate value raised to the power of ops underscore to underscore use, making sure to use modular exponentiation, the power helper function, to handle large numbers and stay within the modulo. We multiply our total underscore score by this result, again using modulo. We decrease k by the number of operations we just used. If k reaches 0, we're done and can return the final score. So is this approach fast enough? Let's look at the complexity. N is the number of elements in the input list nums. M is the maximum value in nums. The sieve part takes roughly om log m time. The 2 monotonic stack passes take oxygen mononitride time each. Calculating contributions takes oxygen mononitride. Sorting the contributions takes on log n. The final greedy multiplication loop runs at most n times, and the modular exponentiation inside takes logarithmic time relative to k, but overall it's dominated by the sorting step. So the total time complexity is dominated by the sieve and the sorting, roughly on log n plus m log m. For space, we need space for the prime scores, om, the scores array, oxygen mononitride, the left-right arrays, oxygen mononitride, the stack, oxygen mononitride, and the contributions list, on. So the space complexity is roughly on plus m. This is much better than the brute force approach. Alright, let's recap the main ideas. First, understanding the prime score was crucial, and using a sieve helps calculate it quickly. The big trick was changing how we looked at the problem. Instead of checking every subarray, we focused on each number and asked how many subarrays it would influence. We used the monotonic stack technique to find the curious of each number based on prime scores. Then, we realized that to get the highest score, we should use the biggest numbers first, so we sorted by value and applied the operations greedily. And don't forget that modular arithmetic is essential when scores get large. Hope this explanation helped you understand the problem and the solution. If you found this useful, you know what to do. Feel free to leave comments if you have questions. And if you're feeling generous, you can support the channel. Thanks for watching, and happy coding!